Well, good afternoon. Thanks for watching. My name is Scott Barrows, and I'm a postdoctoral research associate at the University of Colorado and also a visiting astronomer at Lowell Observatory. And I'll be talking about mid-sized black holes. So the image you see on this title slide is actually an image taken by the Event Horizon Telescope of a supermassive black hole that's at the center of a nearby galaxy. And these supermassive black holes are actually at the massive end of the scale of black holes that we observe in the universe. And there's actually a very wide range of black hole masses that we know about. And so initially, what I'll do is sort of provide some context for that, and describe what we know about black holes and their sizes before diving into this class of mid-size or intermediate mass black hole. So first, we know quite a bit about black holes that are the end products of stellar evolution. So in this schematic you're seeing here on the upper panel, you're seeing what happens to a low mass star, and those ultimately end in the white dwarf stage. But for more massive stars above a certain threshold, they can actually end in compact objects like a neutron star right here, or if the collapsing object is massive enough, it can actually form a black hole. Um, and so these are going to be less than 100 solar masses or so. How do we know about their masses? Well, they're measured when the black hole is in a binary system with another object. And so we can use sort of what we know about physics to infer their masses. And that's sort of shown in this diagram here. So we're actually seeing known masses of compact objects. And so at the bottom, you see sort of masses of neutron stars. And then on the more massive end, you see black holes in X-ray binary systems. So they're orbiting around another compact object or a star. And then even more massive black holes that are actually with detections in masses from the LIGO and Virgo gravitational wave observatories. And what you can see is that you have a range of masses that range from very low to approximately 1 solar mass all the way up to about 80 solar masses. And the masses of these black holes, the end stage of a massive star, is limited by the mass of the progenitor star. And you can see that they don't really go much above 80 solar masses. So that's why we kind of say less than 100 solar masses for a stellar mass black hole in the nearby universe. On the other end, the opposite end of the scale, we have and we observe supermassive black holes. So these are observed to be in the centers of massive galaxies. And so what you're seeing here is a qualitative representation of the correlation between the mass of black holes in the centers of galaxies and the mass of the galaxy itself, or more specifically, the central core of stars in that galaxy. And they correlate very well. And masses of these supermassive black holes are measured in a variety of ways. The best mass measurements are for nearby galaxies, where one can actually trace the motions of stars and gas around the black hole, and again use what we know about physics to infer the mass of the black hole at the center. In doing that, we know that they typically these supermassive black holes in the centers of galaxies are usually at least 1 million solar masses, and can range all the way up to 1 billion or several billion solar masses. And these are when they're growing, they're accreting a lot of material, and that falls onto the black hole and grows it. And as this happens, a lot of that energy is from the created material is released as a luminous energy, electromagnetic radiation. And these can be some of the brightest objects in the universe. And so now that we've talked about stellar mass black holes and supermassive black holes, we can sort of observe them in this sort of distribution of black hole masses. And that's the schematic here, which is created by the NuSTAR collaboration. NuSTAR is a hard X-ray telescope that is very efficient at finding black holes. And so what they're showing here are sort of this mass range of, we have white dwarfs and neutron stars we already discussed, but then stellar mass black holes. And then over on the opposite end, supermassive black holes. And of course, what you might notice immediately is the big question mark in the middle, which corresponds to these mid-sized black holes I was alluding to at the beginning, or what they're typically called as intermediate mass black holes. And you might notice that this sort of class of black hole is supposed to span at least 3 orders of magnitude in mass. And so that in itself makes it an intriguing class of object, but also there's many important reasons why we should be looking for them. And so first I'll say that, while, and the main reason is because they are probably very important for understanding the origins of supermassive black holes. So for example, stellar mass black holes, we know where those come from. We have a good idea about how they form. But supermassive black holes, not so much. It's very likely, however, that they formed from intermediate mass black holes. Okay, so basically you have some black hole in this range, and then it grows over some cosmological time and becomes a supermassive black hole. So that's why it's important to be finding these things so that we can understand the origins of supermassive black holes, which are some of the most powerful objects in the universe. So for the rest of the talk, I guess there's 2 main questions that I'll be focusing on. And they are, where do intermediate mass black holes come from? And 2, where are they now? So the first question, where do they come from? That one is very difficult to answer. So theory provides us with a number of very good ideas that are very well grounded in physics and have an astrophysical context. And so this diagram sort of nicely shows those all in one figure. If you want to learn more about it, you can visit this reference down here. But what this diagram is showing is on the y-axis is redshift. So decreasing redshift is like later in the universe. So the higher the redshift is like very early in the universe. And then on the x-axis is the mass of the black hole in question. So at the very top here in the early universe, there's several different scenarios that theoretically can produce intermediate mass black holes. So this POP3 stellar seed annotation here is implying that intermediate mass black holes can form as the remnants of population 3 stars. So this is population 3 stars are stars that theoretically existed in the very early universe. None of them will exist now in the present day universe, but in the early universe, when there were very few metals in the gas, you could have these very massive population 3 stars that could be up to a few hundred solar masses, and then when they collapse, they can form an intermediate mass black hole. You can also theoretically form intermediate mass black holes from the runaway gravitational collapse of stars and clusters of stars. And so a nuclear cluster of second generation stars, or a nuclear cluster in a protogalaxy. A protogalaxy just being sort of a smaller version of what we know as typical galaxies. And so a collapse of many stars, hundreds of stars, or possibly even thousands of stars, can produce an intermediate mass black hole. And then finally, you can actually have the direct collapse of pristine, i.e., uh, mostly hydrogen gas, that if cold enough will actually collapse and potentially even directly form an intermediate mass black hole without going through a stellar stage. And these red dashed lines here sort of show the different mass ranges of each of these scenarios, and how intermediate mass black holes can be formed. And then you'll notice this big shaded region here kind of shows that along the way, though, the intermediate mass black holes can change their mass, and by growing, either through accretion of material onto them or through mergers or both. And so that's very likely to happen too. And that complicates things, but we'll get to that later. Ultimately, the idea is that they should end up forming supermassive black holes, which are here on the very right-hand side of the diagram. So with this, well, a list of ideas for where intermediate mass black holes come from, I want to ask the second question, where are they now? And the reason why we need to find intermediate mass black holes is, we can't actually see what happened at a redshift of 10 to 12 when these things might have formed. So what we have to do is find them where we can in the nearby universe, or as far out as we can look, and sort of piece together what might have happened to them along the way. So how do we look for them? Well, first I should say that finding black holes can be very difficult sometimes. First, we can only see the material around a black hole. We can't actually see the black hole. And so what that means is we can only see black holes that are actively accreting matter. So if gas or dust or a star gets too close to the black hole, it gets tidally shredded, that material can get really hot as it falls onto the black hole and radiate. And that's how we find black holes. So most will never be found because they're inactive. But we can look for the small subset that are actively accreting. And we can look for those at many different energies. So this figure here is just showing the electromagnetic spectrum, but with multiple observatories corresponding to the wavelength or energy of light that they're sensitive to. And so astronomers have used many of these wavelengths to identify black holes over a wide range of masses, including intermediate mass black holes. So what have they found so far? Well, one idea is that if you just take this diagram on the left here that I showed earlier, that shows how black hole mass correlates with galaxy mass, you might just say, well, if we look for galaxies that are small enough, will the black holes themselves be small and fall in this sort of intermediate range? And the answer is yes, in short. So there are actually a number of, quite a few of these low mass galaxies that are known, and a subset of them actually have actively accreting black holes. And so if you assume that the black hole mass correlates with the galaxy mass, that means that they should host intermediate mass black holes. And so on the right here, I'm just showing a few panels from different studies that have looked for these intermediate mass black holes in low mass galaxies. There are an increasing number of these known, and they're helping us to sort of fill out the mass range of black hole masses that we know about. And so now what I'm showing on the right here is sort of the observational analog of the plot on the left. But creating this plot with the masses of black holes, of intermediate mass black holes that we know about. So those are all the colored points there at the bottom. And so you can see, they're all, mostly below 1 million solar masses, and they more or less sort of fit on this, shaded line, which is that, rough correlation between black hole mass and galaxy mass. But one thing you might notice is that the black hole masses really don't go much below 10 to the 5 solar masses, 100,000 solar masses. And so I guess the question then is this as small as they get, or is this just an observational bias? Are we missing the smallest ones because they're too faint? And the answer is probably yes. We probably are missing a lot of them. We could be missing them because even if the black holes are actively accreting, they're just not massive enough to be bright enough. And it could also be that we are missing many of, we're just not able to find the host galaxies of many of these lower mass black holes because the galaxies themselves are faint. So yes, it's certainly possible that we're missing a lot of these lower mass black holes. Maybe they extend maybe at least 2 orders of magnitude below what we're looking at in this diagram. And so we have to look in other places for them, and people have done that. And so one idea to keep in mind is that galaxy mergers happen all the time. And in particular, many of these low mass galaxies may be accreted onto more massive galaxies. So this is just a picture of different examples of galaxy mergers observed throughout the universe. And you can see that, galaxies can undergo many different mergers, and smaller galaxies can be accreted onto larger galaxies. And so if any of these low mass galaxies hosting intermediate mass black holes are get near a more massive galaxy, they can be effectively consumed by it. And so many intermediate mass black holes may in fact be sort of within more massive galaxies. And there are observational reasons to believe that this is the case. So what we're seeing here on the left is an image of a galaxy that hosts what we call a hyperluminous X-ray source. That red arrow there is pointing at the hyperluminous X-ray source, or HLX, which has a circle by it. And this is actually the first one known, hence the name HLX1. And so it has that name because in X-rays, it's very, very bright. So I've sort of shown a zoom in on a composite color image that includes X-rays. The blue light is X-rays from the Chandra X-ray Observatory, which is an orbiting X-ray telescope. And in X-rays, it's way too luminous to be a stellar remnant black hole. And so it must be more massive than just, what would happen at the end stage of a massive star. We know it's not a background or foreground object. That's been confirmed spectroscopically. So it's definitely a very luminous X-ray source within that galaxy, but not at the center. However, there are too few gravitationally bound stars around it for it to be a supermassive black hole. And the idea there is that if it were another massive galaxy that merged with this one, then you would expect there to be a much more massive core of stars bound to the black hole. But there aren't as many as you would expect. And so that opens up well, makes it very likely that they could be an intermediate mass black hole from a low mass galaxy that merged with this more massive galaxy. And this is probably the case. And so this is actually expected given how frequent galaxy mergers are in the universe, how frequent they are observed to be and predicted to be, especially for low mass galaxies that are satellites of massive galaxies. And indeed, recent numerical and theoretical work has shown that many of these may exist. So these are these images are produced by computer numerical simulations, but they provide predictions for how many of these wandering intermediate mass black holes should be in massive galaxies. Now, keep in mind, we can of course only observe the ones that are active, that are bright. So there may be many more that are orbiting within massive galaxies that we just can't see, and that's what these simulations are showing here. The arrows are just showing the instantaneous direction that the black hole is moving in the simulation, and these two panels are showing just different orientations, viewing angles of the galaxy. And so this is an important prediction because it tells us that there may be many intermediate mass black holes that exist in the universe. They just may be locked up in these sort of orbits within more massive galaxies, and they're hard to find that way. But can we go about finding some of them, and sort of on a large scale, and begin to answer some of these questions about where do intermediate mass black holes come from? So yes, we can. And so that's some of the work that we've been doing recently, is looking for many of these things. And I'm showing here multiple panels of many of these wandering black hole candidates. And so in these two rows, in each row of figures, the leftmost panel is showing an optical image of a galaxy. The middle panel is showing the image of the galaxy through just one filter. It's not a color image. There's just one filter. And then the rightmost panel is showing an X-ray image. So remember, I was saying that the X-rays are one of the ways that we look for black holes. And in fact, black holes are really efficient at creating X-rays compared to other astrophysical phenomena. And so in an X-ray image, they often pop out very nicely. And so you can see in these on these panels on the right, there's actually very few photons. A photon is just the sort of purple magenta color, and they're usually in these images they're clustered around a single point, and that tells you where the black hole is. And they are sort of on the outskirts of these galaxies, very likely wandering around, probably as the result of a merger of a low mass galaxy with a more massive galaxy. So yes, we find many wandering black holes, and some, possibly many of them, are intermediate mass black holes. So now we can take this large sample and sort of, begin to push down a little bit in the black hole mass range, or at least fill it out. So many of these wandering black holes are very likely intermediate mass black holes. That's shown by the purple color coding here. Okay, and many of them are actually probably less than 100,000 solar masses. So these are probably intermediate mass black holes that were very low mass galaxies that have merged with a more massive galaxy and are now orbiting around it. Unfortunately, we're still probably missing the smallest intermediate mass black holes. We're definitely missing all the inactive ones, of course. But the ones that we do find can provide some very important clues as to how they grew up from when they were initially formed and how they might eventually grow into supermassive black holes. So what do I mean by that? Well, let's take a look at this diagram that I showed fairly early on about sort of the theory of where intermediate mass black holes come from and how they grow. So many of them may not just form and sit there until the present day universe. Many of them may grow sort of along this track like this. So, and then eventually we see them. So let's say that we're observing many intermediate mass black holes in this range of, 10 to 100,000 solar masses or so. A lot of these are wandering black holes that have been involved in galaxy mergers, which can really help to grow the black holes just by sort of slamming two galaxies together. That facilitates accretion onto the black hole, which can enhance its mass. And so it's very possible that these the black hole masses that we're observing currently were actually much smaller when they first formed. So what we're sort of looking at is sort of one piece of this puzzle, but by putting it by looking at the context of where we find these black holes, we can sort of infer how they might have grown in the past. And if we find a large enough number of them, hopefully we can start to put constraints on which scenarios happened to form intermediate mass black holes in the early universe, which were more prevalent than others. So with that, there are a few conclusions regarding the question, where are the mid-sized black holes? There are still many open answers though. So first, we know that many are missed due to faintness or inactivity, but we do find a fair number of them. Those that we do find are relatively massive, and this is a observational bias. Of course, we can find the most massive things that are shining most brightly. But we also see that a number of them may have grown substantially from their initial masses due to these merger events. So that means that they may very likely have been much less massive than we're observing them to be now. Many are found in low mass galaxies, isolated galaxies just sitting at the center of the galaxy, but many more may actually be wandering with the outskirts of massive galaxies, just sort of trapped there, maybe wandering for a very long time, because there's really not a whole lot of dynamical friction, which is a force that can create a drag on the black hole to cause it to spiral in. So many of these may just be sitting on the outskirts of these massive galaxies for a very long time. And so finding them can help us add one more piece to this puzzle and hopefully understand where they came from, how they grew, and eventually how they will grow into supermassive black holes. So with that, I want to say thank you for your time and invite any questions if there are any. And while we're waiting for questions, I guess I'll also say that the future of space-based telescopes is actually looking very promising for finding intermediate mass black holes, in particular the James Webb Space Telescope, which is going to allow us to peer very far into the early universe. And we can see some of these very high redshift intermediate mass black holes. And okay, looks like we have a question from someone. Are there any wandering black holes in our galaxy? That's a good question. The answer is very likely yes. Yes. So the Milky Way galaxy is a relatively massive galaxy, much like the ones in the figures I was showing, and so we saw that those are the most likely ones to host many of these wandering black holes. Um, so yes, almost certainly. Looks like we have another question. Could gravitational lensing be used to find inactive black holes? Gravitational lensing is used to find can be used to find massive objects. I don't know how well it would work for intermediate mass black holes, but yes, in theory. We have another question. Any estimates about how many of these there might be per galaxy? That's an excellent question. So the estimates currently just come from simulations, but for massive galaxies, like say the size of the Milky Way, there may be several tens of these actually. We have another question. Why do the sizes of midsize and supermassive black holes correlate with the mass of the host galaxy? Could they be the seeds around which galaxies condensed? So that's a good question, and it's really which came first, the galaxy or the black hole. So to answer the first question, why do the sizes of black holes correlate with the mass of the host galaxy? We can really only hypothesize about that, but they really correlate with the central core of stars in the galaxy. And so there's actually very strong theory to show that that's probably from sort of a hierarchical buildup of galaxies in the universe, right? You have two small galaxies with intermediate mass black holes, and then they merge to form a larger galaxy with a larger black hole, and so on and so forth. But the second question regarding could they be the seeds around which galaxy is condensed is relevant and important, and I think somewhat outstanding still. Okay, looks like we're asking for any last questions. But yes, in the future, I think that our knowledge about intermediate mass black holes will be significantly propelled by the James Webb Telescope and our ability to look further in the universe and find many of these that may not have grown as much from their initial masses. So with that, thank you for the questions.